Hello and welcome to our first online lesson. Hopefully make things clear. Obviously, if you do have questions, please feel free to either send me a message through Google Classroom or you can send me an email. All right, so the normal distribution. We usually say that it's the pattern that's formed by measuring some sort of data from either a population, so a large group, or from a smaller group, i.e. a sample, so long as that's a good sample that better represents a larger population, and that we say it contains some randomness. So when we say randomness, we mean that the data hasn't been sorted or picked before we actually do stuff. Right? We have no impact on which data we're actually measuring. So we want a random sample. We don't want to like pick, let's say we were going to a shop and we wanted to work out the price of products. We're not going to pick the ones that are the cheapest. We're not going to pick the ones that are the most expensive. We're going to do a range, right? And that needs to be a random range, right? We don't want to have any impact on the data that we are measuring. If we were, we would have a skewed sample and it wouldn't be a fair representation of a larger population, right? Our goal in statistics is always to have accurate data. We want it to be the most useful to us, and the way that it's going to be the most useful is if we have a random sample. So for example, if we wanted to look at heights of students at the school, we would obviously need to make sure we measured students from every single year group, 7, 8, 9, 10, 11, and 12, in order to make sure that we had a good sample of all of the students at the school. If we just measured, for example, just the year 12 students, well, we're going to have a very skewed sample. Right? Think about some of the shorter year 7s. We're not going to have anyone in year 12 that's of that same kind of height. So we would need to make sure we had a good representation of all of the students. All right? So not just picking year 12s. So we need to look at the important characteristics of a normal distribution. So the graph of a normal distribution, as you can see there, is what we call a bell curve. Now the reason it's called a bell curve is because, well, it looks a bit like a bell. You're going to see this lots and lots. We're going to look at lots of bell curves over the next coming lessons. At this stage, we're just going to get our head around what it actually looks like. So don't stress too much about having to draw one. The distribution, hopefully you can see there that it is pretty symmetrical. How it curves down on the left is how it also curves down on the right. That middle point where it's symmetrical about is going to be the mean. So there it is there, just putting that dotted line. That is the mean of this group of data. And you can see that that red curve is symmetrical either side of that blue line. If it is a normal distribution, then the mean, the median, and the mode are all going to be exactly the same. So if we think about our bell curve there that we're looking at, the mean is going to be that bit in the middle. So how do we find the mean? Well, that's the average. So we add up all of the numbers together and divide by the total number. So what we're trying to find is the middle. So when we do our mean, if you think of how far to the right the red line is from the blue line at any point, and then you carry along horizontally to the left, you'll see that it's the same distance apart. So if we add a big number and a small number, and then we halve it, well, we're going to get in the middle. If we went 9 plus 11, well, in the middle of that is 10. If we go 0 plus 20, well, middle of that again is 10. So it doesn't matter how far away they are from that middle line is always going to be there as our mean. Median is the middle number, so it should be exactly that. And our mode, well, remember mode is the one that occurs the most. It's the one with the most frequency. So if we were to look at that red curve, it's going to be the highest point of the graph, which lo and behold is again that blue line. All right, so that's one of the characteristics that you will be expected to remember of a normal distribution, that the mean, median, and mode are all the same number. So we can see that that bell curve is nice and thick in the middle and it thins out towards the edges. So what that means is that most of our data, the majority of it, is located in the center. And then as we go further and further away from the mean, we get less and less people that are occurring out there. And if you were to think of, for example, the prices of products, lots of them will be around that middle kind of price. Every now and then it'll be very rare to find something really, really cheap. And hopefully it's not so often that you come across a very, very expensive version of it as well. So that's what we're saying, is that towards the ends, it's less and less likely we're going to find those things, but in the middle, it should be more likely. So let's have a look at an example where we're talking about the height of people. We were looking at it before, so let's look at it again. So as we can see here, we've got some people who are short on the left, people are tall on the right, and then our average height of people is in the middle. So let's say we measure every single student at the school. we would get a bell curve that looked like that. Guaranteed. It occurs almost everywhere in life. So what that's saying is we've got some short people, but not very many. They're going to be like the really short year 7s in there. Likewise, we have some of the tall students who are going to be at the top of the range. But again, there's going to be few of those, let's say some of the really tall year 12s. But for the majority, everyone's going to be around that average kind of height. You think about it, if we were to line everybody up in the class, we'd have a few at the short end, a few at the tall end, but most of the people would be in the middle. And that's generally what you see when you try and line up people by height. There's always that one that says, oh, I'm really short, I'll go at the front. There's that person that says, I'm really tall, I'll be at the back. And then everyone else tries to figure out where they are in the middle because they're all around a similar sort of height. The other thing about our bell curve is what is on our y-axis. So that's going to be the probability that we would find someone really tall, really short, or someone who's average. So as I was saying before, it's not going to be that likely we're going to find really short midgets, and it's not that likely we're going to find really tall giants. Most of the population is going to be in that middle. Obviously, as I was saying before, with randomness, we can skew our data. We could go to a basketball tournament and measure everyone at the basketball tournament. We would still have a bit of a bell curve, but it's going to be primarily up towards the tall end. All right, so it's not quite so random because we're picking where we want to get our data from. All right, we need to have a random sample. Now, we have looked at standard deviation before, and what standard deviation is, it's talking about how far something is from the mean, how spread out our data is. Deviation, how far we have deviated from or how far away from our mean we are. This leads to the 68, 95, 99.7 rule. And I will explain that in just a minute, exactly what that means. So with our normal distribution, our mean is nicely in the middle of our normal distribution. So what that means is that it gives us a nice symmetrical distribution. 50% will be to the left or below the mean, and 50% will be to the right or above the mean. So if I had a collection of scores, if it's a nice normal distribution, half of those scores are below the mean and half of those scores are above the mean. If I go one standard deviation above and one standard deviation below the mean, I get an area in the center. Now that area in the center, that is one standard deviation either above or below the mean, will contain 68% of all my results. So if we have a population of scores, 68% of those scores will fall within one standard deviation above or below the mean. On the diagram there, if I've got 68 in the middle because it's nicely symmetrical, the remaining 32% is going to be split up with 16 below that section and 16% above that selection. But in that one bit in the middle, which is one standard deviation above and below the mean, we're going to have 68%. Now, if I go out to 2 standard deviations, what that now means is that from 2 standard deviations below the mean to 2 standard deviations above the mean, I now have 95% of all my scores. So of a population, 95% will be within 2 standard deviations either above or below the mean. Again, being symmetrical, the remaining 5% is going to be split to 2.5% on that left tail of the diagram, and the other 2.5 is going to be on the right tail of the diagram, just those little bits on the side. Now, this is the 68, 95, 99.7 rule. So if one standard deviation gives me 68%, 2 standard deviations give me 95%. Hopefully you can figure out what 3 standard deviations is going to do. It's going to give me 99.7%. So almost 100% of my data will be within 3 standard deviations above the mean and 3 standard deviations below the mean. It's not quite 100%. There's always just that little bit that's beyond that, certainly with a large population. So what we've left is with 0.3%. So we're going to split that in half again. 0.15% is going to be below 3 standard deviations in that little tail on the left, and 0.15% of the population will be above 3 standard deviations in that little tail on the right. All right, example 2. So in a normal distribution, the mean recovery time after contracting a certain disease is 12 days with a standard deviation of 2 days. A, how long would it take for half of the patients to recover? Well, we know that our normal distribution is nicely symmetrical. So our mean is going to be in the middle, and we're going to have half above that and then half below that. So we know that our mean is 12 days. So how long will it take 50% to recover? Well, it's going to be 12 days. 50% below the mean, 50% above the mean. Mean is 12 days, so we're going to get half of them recovering in 12 days. Some might be less, but that's still within 12 days. B, what percentage of patients would recover within 8 to 16 days? Well, we know we've got a mean of 12 days and we've got a standard deviation of 2 days, so we need to work out where are 8 and 16. So one standard deviation above 12 is going to have 14, and one standard deviation below is going to be 10. Two standard deviations, well, that's going to be 4 is 2 standard deviations, so 12 take 4 is 8, 12 plus 4 is 16, so that gives me that section of 2 standard deviations. And remember, 2 standard deviations lines up with the 95 from our 68, 95, 99.7 rule. So how many will recover between 8 and 16 days? Well, that's going to be 95% of our patients. There's going to be 5% that are still outside of those 2 standard deviations. So that covers those that are going to recover with less than 8 days and those who are going to take more than 16 days to recover. C, what percentage of patients would recover within 10 days? Now, we've got our 10 days. There was one standard deviation, right? One standard deviation from the mean was 10 to 14 days. So if I just bring up a little diagram there, that's it there with our one standard deviation. The part that we are interested in is those patients who recover in less than 10 days. So our mean in the middle is 12 days. One standard deviation to the left is 10, but I want to know everybody who's less than that 10. So looking at that diagram, I'm talking about that shaded area on the left tail that says 16%. Because those represent the patients who would recover in less than or up to and including 10 days. So what percentage? It's that 16% on the left tail there, because that's at the lower end. D, if we've got 400 patients who have contracted the disease last year, how many would have recovered within 16 days? Now, our 8 to 16 days, that was 2 standard deviations. So let's change the diagram to represent our 2 standard deviations. We've got our 95% in the middle, but the question says how many have recovered within 16 days. So that bit in the middle is just 8 to 16 days, but I want those people as well who are less than 8 days. So it's going to be that 95% in the middle plus the 2.5% on the left, because all of that is less than 16 days. So we're going to do 95 plus 2.5, so that's going to give me 97.5%, but then I need to work out what is 97.5% of 400 patients. All right, so 2.5% plus 95%. Now remember, if you're doing this in a calculator, you're going to need to do 2.5 plus 9.5 equals 97.5. Divide that by 100 to convert from a percentage to a decimal, and then times that by 400. And that's going to give us 390 patients. So 390 patients last year not only contracted the disease, but recovered within 16 days. The other way that you could do this on a calculator is because it doesn't really matter where you divide by the 100. You could just do, well, 400 divided by 100 is 4, and then go 2.5 plus 95 is 97.5. 97.5 times 4 is 390 patients. You will get the same answer working that way. Example 3. The distribution of delivery times for pizzas made by Antonio's Pizza is approximately normal. So that's telling us that we have a normal distribution, approximately. with a mean of 25 minutes and a standard deviation of 5 minutes. So the first thing we want to do is draw a bell curve to represent the delivery time distribution. So when we come across that question, what we want to do is we draw ourselves that normal bell curve shape, but rather than just have mean and then 1 standard deviation, 2 standard deviations, we actually want to use the numbers. So in the middle of our bell curve, we are going to write 25. And then we're going to go up by 5 minutes and down by 5 minutes. So we're going to have 25 in the middle, and then we're going to go up to 30, 35, and 40. And then we're going to go down to 20, 15, and then 10. And we're going to get a diagram that looks like that. I've written in that 68% is what's going to be between 20 and 30 because that's our middle part of our normal distribution. The 13.5s on either end, if you go 68 plus 13.5 plus 13.5, that will all equal 95%. So that's just breaking down that 95% from 2 standard deviations above and below into those 3 sections. There is a section to the left of 15 and a section to the right of 35 that don't have numbers in them. If we need them, we can work them out when we get there. All right, but in essence, all we've done is we've drawn the normal distribution curve and then written in the numbers from the question. And that just has to be a sketch. Don't be too upset if your curve isn't perfectly symmetrical when you draw it. So then what percentage of pizzas have delivery times between 15 and 35 minutes? Now, because we've nicely written all of our times onto our bell curve, we can just read it straight off the diagram. So between 15 and 35, well, that's 2 standard deviations. So we just want to know what's between those 2 standard deviations. So you can add 13.5, 68, and 13.5, or you can remember that it's 95%, doesn't matter which, but that's our answer. 95% of all pizzas have delivery times between 15 and 35 minutes. That should say C, not B. What percentage of pizzas have delivery times greater than 30 minutes? So remembering that our distribution is nicely symmetrical. If I was to draw a line between 25 and 30, everything to the left of 25 is going to be 50%. Between 25 and 30, I've got half of that 68, so that's going to be 34. So everything to the left half is 50 plus another 34 is everything up to that 30-minute area. So if I go 50 plus 34, well, that's going to give me 84. That's everything less than 30 minutes. But I want to know what's greater than 30 minutes. Well, we've just worked out what the percentage of less is, so it's going to be 100 minus that. So that leaves us with 16% unaccounted for. So that's the percentage of pizzas that had delivery times greater than 30 minutes. All right, now you can, like I said, it's 50% is going to be to the left and 50% is going to be to the right of that 25 minutes. So you can say, well, we've got 50 minutes to the right minus 34, and 50 minus 34 is again 16. So it doesn't matter which way you go, you will still get the same answer. It's all about just working out what part of our normal distribution are we interested in finding. The normal distribution is on your reference sheet, that the bell curve with the percentages. So you don't have to remember that. You just have to remember what part of that diagram represents which part of specific questions. So that when you get a question like this, you say, well, it's the greater than 30 minutes, and you could shade in the section that represents greater than 30 minutes, if that helps you, to then try and work out what the percentage is going to be. And that says C, but really should be D. In 1 month, the House of Pizza delivers 2,000 pizzas. Now, assuming they have the same distribution as Antonio's Pizzas, how many of these pizzas are delivered in less than 10 minutes? So remember how we had our 68, 95, 99.7? So that 99.7 covers every pizza delivered between 10 minutes and 40 minutes. So that left us with 0.3% for both less than 10 and greater than 40. So we want to half that to 0.15%. So 0.15% of all pizzas are going to be delivered in less than 10 minutes. And realistically, that should make sense, because think about, this is from you ordering it to how long it takes them to make it to then delivering it. 10 minutes, that's pretty quick. Your pizza wouldn't be cooked. So for whatever reason, we've got 0.15% of 2,000 pizzas. So you can go 0.15 times 2,000 divided by 100, or 0.15 over 100 times 2,000, or 0.15 times 20. It doesn't matter which way you get there, it's still going to be 3 pizzas. So out of those 2,000 pizzas, there's only 3 that were delivered in less than 10 minutes. And that brings us to the end of the presentation.